Now, what is a rate limiter? Let me explain this concept in a fun, relatable way. Imagine you are at a popular amusement park and there's this super exciting roller coaster that everyone wants to ride. Now, to keep things fair and ensure that everyone gets a turn, the park has a rule. The rule is that every person can ride the roller coaster only twice a day. At the entrance, a security guard is standing, keeping track of how many times each person has ridden the roller coaster. If someone tries a third time, the guard says, "Sorry, you have hit your limit for this day." This system prevents anyone from riding too many times and allows more people to enjoy the experience. How does this relate to rate limiting? In the world of software, the security guard is like a rate limiter. Its job is to track the number of requests coming in from the users. Now, just like the roller coaster, there is a limit on how many times a user can perform an action, like sending a request to the server in a specific time period. For example, if we allow only 2 requests per user per second, once a user hits that limit, the rate limiter steps in and says, "Sorry, you have reached your request limit for now. Try again later." Now, in the last lesson, we have seen that a rate limiter is just like a security guard. Security guard is at the entrance, keeping track of how many requests are being sent by each user. If these requests exceed a certain threshold, then the security guard would disallow these requests. For example, on a platform like Instagram, a rate limiter could be in a place to ensure that no user can post more than 100 times a day. This kind of control helps prevent any single user from overwhelming our system, with excessive activity. This ensures a fair usage and smooth performance for everyone. Why do we need a rate limiter? First, it prevents overloading. Now, without a rate limiter, too many requests at once can overwhelm a system, causing it to either crash or maybe perform poorly. A rate limiter steps in to cap these number of requests and keep everything stable. Second, it ensures fair usage. Imagine one user constantly spamming the system with requests. This can block other users from using the service. A rate limiter ensures that all users get an equal opportunity to access the system resources. Third, control costs. More requests mean more processing power and definitely higher costs. A rate limiter helps manage this by restricting excessive usage and keeping processing costs under control. That is why the rate limiters are an integral part of system design, balancing performance, fairness, and cost efficiency. Now let us take a look at the functional requirements for our rate limiter system. Our system must be able to control or quote-unquote limit how many requests a user can make within a specified time period. Now, this limit could be based on IP address. For example, we can restrict each unique IP address to just 100 requests per minute. It could be based even on user ID. For example, user 123 is allowed just 50 requests per hour. It could even be based on device ID. Imagine limiting each unique device to just 500 requests per day. We can even limit based on session IDs. Now, this is the first and the most important feature requirement from our rate limiter system. Second, we want to support user notification. If a user exceeds the allowed limit, then our system must notify them. For example, if a user sends their 101th request in a minute, they will receive a message saying, "You have exceeded the request limit, please try again later." Let us now move to the non-functional requirements for the rate limiter. First is our system should be highly available. Precisely, we should aim for 99.99999% of the uptime, which is 7 nines. Now, this would help to ensure we have minimal downtime and an uninterrupted service. Second is low latency. Now, one thing to note is that the rate limiter system will act as a subsystem in a larger system. So it could be a part of perhaps a social media service. It could perhaps be a part of an e-commerce service. So effectively, it's a part of a larger system. Now you can imagine that if this rate limiter system has delay, this would ripple throughout the whole system, slowing down the overall performance of the complete system. Therefore, the rate limiter must be designed in such a way that it works quickly and efficiently. Third is cost effectiveness. By similar reasoning, where we said that a rate limiter is a part of a larger system, we can say that if the rate limiter system is not cost effective or it is expensive, then it would increase the overall costs of our complete system. Therefore, running the rate limiter system, we should make sure that we have included the cost effectiveness angle into perspective. Let's now dive into the capacity estimation for our rate limiter. We'll start with estimating the number of users. This is important because this would give us a sense of overall scale for our system that would help us to estimate the throughput, storage, memory, and network bandwidth. We'll estimate that we have around 500 million users that will be using our service on a daily basis. These are the users that are making requests every single day. Over a span of month, our system is expected to serve around 2 billion unique users. So our monthly active users, quote unquote MAU, is 2 billion users. This numbers reflects the total reach of our platform across a month. With these numbers in mind, we can proceed to calculate the throughput, storage, memory, and network bandwidth. Stay tuned for the next one. To estimate the throughput, let's assume that each user makes an average of 100 API requests per day. We already know that we have 500 million daily active users. Now, if we have 500 million daily active users and each user is going to make 100 requests per day, then the total requests per day would be 500 million multiplied by 100 requests per day. This would amount to 50 billion requests per day. So this gives us a clear idea that our rate limiter needs to handle up to 50 billion requests every day. This helps us give a guide on how we can design for scalability and efficiency. Let's now discuss the storage and memory requirements for our rate limiter. Now for rate limiting, what kind of data do we need to store? We mainly need to store the counter data. Now what is the counter data? This data tracks the count of each type of request that is currently made by users. So by counting these counts or by seeing that this count is below the threshold, we can decide whether we do not need to rate limit or whether we need to rate limit. For example, if this count reaches beyond the threshold that we have set, that is the allowed request limit, then we rate limit that particular request. You can see in the table that this data is per user per API. What does this mean? This means that for every user, we would be storing the counters for all the different types of APIs the user is leveraging. You can see user 1. For the request type, number of posts per day, the counter is 4. Similarly, second record, again for user 1 but different API. This request type is number of friend requests per hour and the counter is 3. Similarly, user 2, this time a different user. The API is again number of posts per day and the counter is 3. Now, let us estimate the storage. Let's assume on average that one entry in the counter table requires 100 bytes of storage. Now suppose that our system supports 50 different API types or request types. Now for all of these request types, we have to store the counter data for every user. So for every user and for each type of request for that particular user, we need to store the current count. Now using this, we can say that the total storage required would be the number of entries in this table and then multiplied by the size of each entry. Now we already know that the number of entries would be nothing but the total number of users, and for every user there is a different API type, and we know that there are 50 different API types or request types possible. Therefore the total number of records would be total number of users multiplied by total number of different API request types. So 500 million users multiplied by 50 request types. And then we ultimately multiply these total number of records in the table by the size of each record, which is 100 bytes. So this comes out to be 2.5 terabytes. Now one thing to note that This amount of storage is actually manageable by modern caching solutions, meaning that we can store the entire counter data in cache without significantly affecting the system performance. Also, since our latency requirement is quite low and the storage size is reasonable, caching the counter data is actually an efficient approach to meet our storage needs as well as our non-functional requirement of low latency. Let us now move to the network bandwidth estimation. Now, the network bandwidth estimation tells us how much data is flowing in and out of our system per second. Now, to calculate this, let us make some assumptions. Firstly, we would need to consider the size of the data that is transferred with each request and response. Let's assume that on an average, each request and response combined, they have a size of around 1 kilobytes. Also, we previously have seen that the total number of requests per day is 50 billion requests. So it's simple, right? The total data transferred in a day would be the total number of requests in a day multiplied by the size in each request. That is the size of the payload in each request, which is around 1 kilobytes as we have assumed. Therefore, the number would be 50 billion requests per day multiplied by 1 kilobytes per request. This amounts to 50 terabytes per day. So this is the bandwidth requirement per day. In order to convert it into per second, we just divide it by 24 multiplied by 60 multiplied by 60. So this amounts to 161 megabytes per second.
Now in system design, where we place our components is just as important as what they do. Now when it comes to a rate limiter, the question is, where should it reside? There are two options primarily for this. Option 1, placing the rate limiter before the API servers. Option 2, placing the rate limiter in the API servers or with the API servers. Now let us look at each of these options and see their advantages and disadvantages. Now in the first option where we are talking about placing the rate limiter before the API servers. Now in this case, it means that we are effectively controlling the traffic before it is reaching the API servers. Now what could be pros of this design? First pro would be enhanced security. Why is that the case? This is because since the rate limiter filters the traffic before it reaches the API servers, any malicious or excessive traffic would be blocked early. This means we have improved the security of our system. Second is reduced load. Now the API servers will only handle legitimate requests. Therefore, their overall workload would be reduced since some of these illegitimate or extra or malicious requests would be filtered by the rate limiter early on. Now the primary con would be increased latency. Now when we are placing the rate limiter before the API servers, we are effectively adding an additional processing step in our overall design. This means that we need to have more time for each request to be handled, potentially slowing things down. Second con would be single point of failure. Now since all the traffic would pass through the rate limiter, if in case the rate limiter goes down, no traffic can reach the servers, which could bring the whole system to a halt. Now let's look at the option 2 and see its advantages and disadvantages. Option 2 was placing the rate limiter with the API servers. Now in this setup, the rate limiting happens on the API servers itself. Basically, the API servers would also have the rate limiting logic. Now what would be the pros of this approach? The first pro of this approach would be granular control. Why is that the case? This is because each server or service can have its own custom rate limiting. This would allow for more specific configurations based on different servers or services, giving a more granular control. Second, there is no central point of failure here. Now, since each server handles its own rate limiting, there is no single point where the entire system could collapse. What would be the cons of this approach? The primary con would be increased server load. Why is this the case? You can see that in the server logic also has to encompass the rate limiting logic. The servers will now have additional responsibility to handle the rate limiting on top of their regular tasks. This could definitely increase their workload. Now, which approach is better? It depends on our system. For centralized control and enhanced security, the first option is better. That is, we have to place the rate limiter as a separate component before the API servers. If you perhaps need more control per service and want to avoid a single point of failure, then placing the rate limiter with the API servers or in that API servers is ideal. For our discussion, going forward, we will go with the first option. We will place the rate limiter before the API servers.
Basic high-level design flow of a rate limiter. Now, step 1. It all starts when a client sends a request. No surprises. This could be an API call from an app or a browser requesting for the data. Step 2. Before reaching the server, the request is checked by a rate limiter. Here's what happens exactly here. Now, the rate limiter is keeping track internally of how many requests the client has made. If the client has already hit the limit, let's say the limit is 100 requests in a minute. If this is the case, then the rate limiter would drop the request and would not let it pass through. If the request count is below the limit, then the request is allowed to proceed. Step 3. Once the rate limiter allows the request, it goes to the API server. The API server processes the request and sends a response back to the client. Now, this is a super high-level flow of the rate limiter system. Oh, by the way, a fun fact. If a client exceeds their rate limit, the rate limiter would disallow that request, and it will also respond with an HTTP status code of 429. Now, what is 429? This means too many requests. This basically lets the client know that they have hit their request limit and need to wait before trying again. Now, we have already seen in the last video that when a client sends a request, it first reaches the rate limiter. And then the rate limiter would decide whether to allow or block this request. How is this decision going to be made? This decision would be based on the number of requests made by that client in a specific time frame. We can call this as the request counter. Now, if this request counter is below the allowed limit, the request is forwarded to the API servers. If it's above the limit, then the request would be dropped. Now, an interesting question here could be, where are we actually storing this request counter? Could it be in a database? Well, databases are too slow for this type of frequent check, given that we'll be doing this for all the users for all their APIs. How about a cache? Cache would be perfect because a modern cache solution, let's say Redis, is fast and efficient for storing small pieces of data like request counters. This would allow the system to handle millions of requests quickly without any delays. Now, in the diagram, you can see I have updated. First, the client sends a request to the rate limiter. Second, the rate limiter checks the current counter in the counter cache for that client on that API. So basically, if let's say the client is using a specific API, so we are maintaining a counter for the number of requests made by that client. So we check the current number in the counter cache. Currently, it is 4. So we increment it by 1 to also include this incoming request and then update it to 5. Now it also checks if 5, which is our most recent counter value, whether it has exceeded the threshold or not. If it has not exceeded the threshold, then the request is allowed to reach the API servers. Otherwise, it gets dropped. The client request first reaches the rate limiter. The rate limiter would then decide whether to allow or drop the request. How would it decide? It would check the current request count in the counter cache, update it by 1, and then check this updated value against our limit. We already know that these counters are stored in our counter cache, but where is the limit stored? Now let's explore this in this video. The limit is stored in something we call as the roles DB. You can see in the diagram that we have stored the limits for different types of requests here. Like if it's a create post API, then we have the limit as 100 posts per day for every user. Or perhaps if it's a comments API, the limit is 500 comments per day for every user. Similarly, our roles DB is going to store all the threshold values for different types of requests or quote unquote rules as we call them. Now we also have an associated rules service. What will this rule service do? It will just update these rules also in the rules cache, periodically. This is because we can access these rules faster from a cache versus a database. Now let's see how the overall flow looks. The client, perhaps this time, sends a create post request. This request first reaches the rate limiter. The rate limiter gets the corresponding rate limiting rule from the rules cache. Now, since it's a create post API, we fetch the posts limit rule. And we see that the limit for this is actually 100. The rate limiter then gets the request count from the counter cache. Let's say it is 4 for now for this client. The counter is then updated to 5 to include this new request type and then stored back in the cache. The rate limiter also checks if this updated counter value of 5, is it more than our limit of 100? Is it less than our limit of 100? Now, since 5 is less than 100 or our counter is below the threshold, the request is forwarded and allowed. It reaches the API servers for further processing. If the request counter would have perhaps exceeded our limit, let's say the user would have sent 101st request, then the request would have been denied. Now we have touched the rate limiting on a super high level in the context of the high level design diagram, but we have not actually taken a look at the algorithms that how do we actually implement these rate limiting. So the core logic behind rate limiting can be implemented using 5 algorithms. First, the very popular one, the token bucket algorithm. Second would be the leaky bucket algorithm. Third would be the fixed window counter algorithm. Fourth would be the sliding window lock algorithm. And fifth would be the sliding window counter algorithm. Let us now move to our first algorithm for the rate limiting, which is called as the token bucket algorithm. Now, the token bucket algorithm is very simple and very intuitive to understand. There are only a couple of things involved here conceptually. First is a bucket. What is a bucket? You can think of a bucket as a container that can help us to store coins. And yes, the maximum number of coins that you can store in a bucket is given by the bucket capacity. So if the bucket capacity is 3, we can store a maximum number of 3 coins in the bucket. The second thing is bucket refiller. So there is a bucket, and then the second thing is a bucket refiller. As the name says, the purpose of the bucket refiller is to refill the bucket with a particular rate that we set. For example, if we set it to 60 seconds, then it means that every 60 seconds, the bucket refiller would be able to fill the bucket to its fullest capacity. Now let's take an example to understand this algorithm and how this works. We will be using this bucket, the coins, and the bucket refiller to draw an analogy between our actual algorithm and this conceptual model. So first, any request that passes through our system or any request that is allowed through our system needs to consume 1 coin in order to pass through. So for example, if the bucket has 2 coins, then 2 requests can pass through because each of the requests will consume 1 coin. Second thing, the maximum number of coins a bucket can hold is given by the bucket capacity. Let's say the bucket capacity is 3. So we can say that the maximum number of coins that the bucket can hold is 3. Third thing, whenever the bucket gets empty or there are no more coins in the bucket. Now, if that's the case, no further requests would be able to pass through, because any request that needs to pass through needs a coin. And if the bucket is empty, there are no coins, then no request can pass through. So let's take a look at these diagrams. We look at it chronologically from t equal to 0 till t equal to 130 second and understand the complete algorithm, how this works. Let's say at t equal to 0, our bucket is refilled. Now this bucket is refilled every 60 seconds. So at t equal to 0, this bucket is refilled. So we have 3 coins in this bucket at t equal to 0. Now let's say at t equal to 30 seconds, 2 requests come. So if the 2 requests are coming and they need to be allowed or passed through, then definitely these 2 requests would need to consume 2 coins, 1 coin for each request. So effectively at t equal to 30 seconds, these 2 requests come and they consume 1 coin each. So 2 coins are taken away. So right now at t equal to 30 seconds, we just have a single coin remaining in our bucket. Now at t equal to 45 seconds, there is one more request that comes. So one more coin is taken away. Let's say at t equal to 50 seconds, there is one more request that comes. Now what happens? Because the bucket doesn't have any coin. Now if this is the case, we already know that a request needs a coin to pass through. Therefore, this request would be not allowed. In other words, it would be rate limited. So this request is rejected. So in short, in the span of first 50 seconds, we allowed 3 requests to pass through. The 4th request was rejected. Now we come to our refill time, which is t equal to 60 seconds. So at t equal to 60 seconds, 3 coins are refilled back in the bucket. So our bucket is full and is containing 3 coins. Let's say there is one request that is coming at t equal to 70. So would it be passed through or would it be rate limited? It would be passed through. Why? Because we have sufficient number of coins in our bucket for this request. This request just is one request and it needs just 1 coin. And therefore, it consumes that coin and then it passes through the bucket. Now we come to t equal to 120 second. Now at t equal to 120 second, our bucket is refilled. Now we already have 2 coins in our bucket and our refiller is trying to fill 3 more coins into it. So the surplus 2 coins would be overflowed and 1 coin would be refilled, making it a capacity of 3. In other words, our bucket cannot accommodate more than 3 coins at any time. It is its maximum capacity. Let's say we come to t equal to 130 second. Let's say there are 3 simultaneous requests coming at t equal to 130 second. Now would all these requests would be allowed or would they be rate limited? Or perhaps would some be allowed and some be rate limited? All of these requests would be allowed because we have 3 coins which are sufficient for 3 requests. Now this is pretty much how the algorithm works. Trust me, if you have understood this conceptual analogy, you have pretty much understood how the algorithm works. Whenever the request was able to consume a coin and pass through, it means on a rate limiting level that that particular request was not rate limited because it was passed through, it was allowed. Whenever we didn't have sufficient number of coins in our bucket, for example at t equal to 50 second when our bucket was empty and there was one request. Now in such cases, the request is rate limited. So this kind of makes sure that every 60 seconds we just have 3 requests that are allowed. So every 60-second window we have 3 requests that would be allowed to pass through. The rest would be rate limited. Now let's understand what are the pros and what are the cons of this algorithm. Everything has pros and cons. Firstly, it is very simple and very intuitive to grasp, that you must have felt. Secondly, it is memory efficient. What do I mean by this? Now let's say you try to implement this algorithm. You actually try to write the code. What would be the parameters that you would be using, or what would be the variables that you would be using in your code? Specifically for this algorithm, there are 2 parameters or 2 variables required. One is the bucket capacity and second is the refill rate. Now, whenever we try to implement this algorithm, there are just 2 primary parameters that we use, the bucket capacity and refill rate. Therefore, we don't need to store much in our memory when we are trying to implement and when we are trying to run this algorithm. And therefore, it is memory efficient. It's just two variables that we need to keep track of in the memory. Third, this algorithm allows burst or sudden traffic. You have already seen this. We have seen at t equal to 130 seconds, there were 3 simultaneous requests. So 3 simultaneous requests came and all 3 were allowed because our bucket had sufficient number of coins to allow them. So this means that this algorithm would be able to handle burst of traffic or sudden increase in traffic, which actually happens in reality sometimes. Now let's come to the cons of this algorithm. The only main disadvantage of this algorithm is we have to choose the right values of two parameters, which is bucket capacity and refill rate. We cannot keep the refill rate too high or too low, nor we cannot keep our bucket capacity too high or too low. We need to have a balanced or a sweet spot for the values of these two parameters. Now this in practice is very challenging to determine. Let's now try to understand the leaky bucket algorithm. The most intuitive way, no surprises, to understand or to visualize this algorithm is to actually imagine a leaking bucket. Now, what is a leaking bucket? Imagine you have a bucket. There is a hole in that bucket. You have a tap and water is flowing from the tap into our bucket. Now, let's try to conceptually draw analogies. Firstly, all the incoming water from the tap that is entering into our bucket would represent all the incoming requests to our system. Second, all the outgoing water from the hole. If there is a hole, definitely it is leaking some water out. So all this leaking water or outgoing water represents the requests that are processed, that are successfully allowed. Third, there can be a scenario when the tap water, the water from the tap is flowing very quickly. So there would be an overflow in our bucket. So in those scenarios, this overflowing water from the bucket would represent all the requests that are dropped or quote unquote rate limited. Also, the bucket represents the processing queue. Now let's walk through one scenario and try to understand this with the help of a diagram and example. Let's say you have a queue. The queue can hold up to 6 requests at a time. So effectively, the queue has a capacity of 6. Also, the processing rate of this queue is 4 requests per minute. So every minute, it takes the first 4 requests from this queue and then it processes them, or you can say it allows them. If our queue is already full, then there can be no more further requests that can be added. Basically, all those requests would be rate limited. So let's walk through one scenario to understand this. Let's say at t equal to 0 second, we have one incoming request. This green request. Now at this point, the queue is empty. So this green request would be added to our queue. Let's say at t equal to 30 second, we have 2 more incoming requests. This orange and the pink. Now as there is space in our queue, these 2 requests would be added to our queue. Let's say at t equal to 45 seconds, there are 3 more incoming requests. The purple, the blue, and the yellow. We have space for them in the queue. So all of these 3 requests would be added to our queue. Right now, our queue is filled to its fullest capacity. Now we come to the t equal to 60 second mark. Now here, we have completed 1 minute. Therefore, we would be processing 4 requests because we are processing the requests at a fixed rate of 4 requests per minute. Therefore, the green, the pink, the orange, and the blue requests would be processed and would be taken out from the queue. Now let's say at t equal to 70 second, we have 5 more incoming requests. Now, we have a space of 4 remaining in our queue. So 4 requests
could be added to our queue, and therefore they get added. The fifth request, there is no space for that request in our queue, and therefore that would be rate limited. Now, this is pretty much how our leaky bucket algorithm works. To summarize, we have processed 4 requests every minute. We also have a queue where we can store some extra requests that we can process later. If the incoming requests count is much more than what can be accommodated in our queue, then we simply discard or rate limit those requests. Now let's draw some contrast with our token bucket algorithm that we have studied earlier. In the token bucket algorithm, as you can recall, only as many requests were allowed per minute as there are number of available tokens in the bucket. So if your bucket has a capacity of 5 tokens, then only 5 requests were allowed in 1 minute. Anything beyond that is straight away discarded. However, in the leaky bucket algorithm, as you have noticed, even though our processing rate is 4 requests per minute, we didn't immediately discard the extra requests, the 5th and the 6th request. In the diagram, you can recall the purple and the yellow requests. Instead, they were added to our queue for further processing. So this is pretty good because we are effectively not dropping every extra request. We are actually holding them in our queue and we can process them later. So we can ensure that valid requests are not just randomly thrown away. Instead, we can save them for the processing later. However, this thing itself can turn into a disadvantage. How? By queuing up extra requests and then carrying them forward for processing in the next minute, we are actually unintentionally introducing delays for the new incoming requests. Let me give you an example to clarify. Let's say our queue has a capacity of 1000. Also, the processing rate is 50 requests per minute. Now let's say the first minute we get 1000 requests. Now all these 1000 requests would be added to our queue. The first minute completes and we have processed the 50 requests. So we have 950 requests that are remaining in our queue to be processed. Now let's say in the second minute we have 50 more requests. Now our queue has a space of 50. So these new 50 requests would be added to our queue. But these would be waiting behind the older 950 that are already present in our queue. So all this 50 new requests that we got in the second minute would take a lot of time to be processed because the 950 requests that were in our backlog from the last minute, they have to be processed first. So the incoming new requests could be delayed because we have this queue which is effectively acting as a backlog. Let's now move to the fixed window counter algorithm. Now the fixed window counter algorithm is also very simple and intuitive to grasp. As the name says, we have fixed windows. So the time is divided into fixed windows. In the example, you can see that we have chosen that window to be of 60-second length. So we have the window 1, which is from 0 to 60. We have the window 2, which goes from 60 to 120, and so on it continues. Now in every window, we have a certain limit that we set. This limit tells how many requests at the maximum would be allowed in that window. So if the number of requests would exceed this limit, then all the extra requests would be rate limited. And yeah, one more thing. After each window, or essentially at the beginning of every window, our counter is reset. So let's understand all of this with the help of an example. In the diagram, you can see that we have a window size of 60 seconds. Also, our limit is 5, so we allow 5 requests every minute at the maximum. Now in the first window, 3 requests came. So all of these 3 were allowed because these 3 were within our 5 requests limit because 3 is less than 5. We move to our next window. Now, one thing to note is at 60 seconds, as I already mentioned, before the start of our second window, the counter is reset. So we start counting from 0 again.
Now in the second window, we have got 6 requests. Now the first 5 would be allowed because they are within our limit, but the sixth one would be rate limited. The rate limited requests are marked by red and the allowed requests are marked by green. Similarly, this pattern would continue for every window. You can see in the third window, we just had 2 requests, so both of them were allowed. In the fourth window, we had 7 requests. The last 2 of them were rate limited and the first 5 were allowed. So this is effectively how our fixed window counter algorithm works. You can observe that unlike the leaky bucket algorithm, where extra requests were queued for further processing later, this algorithm would just drop the extra requests outright. Also, there is one fundamental problem with this algorithm if you notice very closely. I'll give an example so that you can understand better. Now let's say that our rate limiter, hypothetically, allows up to 6 requests per minute. So our fixed window counter algorithm has a limit of 6 requests every minute. Let's say at t equal to 50 seconds, the system receives 5 requests. Now, all of these requests would be allowed because within the first 60 seconds, we have got just 5 requests and 5 is less than our limit of 6. Now, let's say that at t is equal to 70 seconds, just after our window resets at t equal to 16. So at t equal to 70 seconds, let's say our system receives 5 more requests. Now, would they be allowed or would they be rate limited? They would be allowed by this algorithm because in our second window, where we have already reset the counter, we just have 5 requests and 5 is less than the limit of 6. So effectively, if we run this algorithm, all of these requests would be allowed. But if you think about it, from a period of 50 seconds till 70 seconds, 10 requests were accepted by our rate limiter. So basically, within 20 seconds, we had 10 requests that came and all of them were accepted and not rate limited. Now, we also know that conceptually, we have a limit of 6 requests per minute. Do you see the issue here? Basically, the requests that are arriving at the edge of the window, they could bypass our limit. Let's say if a burst of requests arrive at the edge of our window, as we saw, at 50 seconds, we had 5 requests. At 70 seconds, we have 5 requests. All of them were allowed, bypassing our rate limit of technically 6 requests per minute. So just to summarize, the advantage of this algorithm is that it's very easy to implement and understand. And the disadvantage is that it allows burst of requests at the edges of the window, which might overload the system for short periods. Now let's take a look at the sliding window lock algorithm. The sliding window lock algorithm is an improvement over the fixed window counter algorithm. You might remember from the lecture on fixed window counter algorithm that we had fixed window sizes of 60 seconds. And then we had set a limit on the maximum number of requests that are allowed within each window. Now it worked nicely, only except an issue where someone could exceed our maximum limit by squeezing or sending his requests near the edge of the window. Now this algorithm addresses that issue. How does it address? It's simple, just by keeping a sliding window instead of a fixed window. Now this sliding window would always look back from the current time to the window size. Let's say it is 60 seconds. And then when it looks back, it would count the total requests in that window. This is to decide whether to allow or rate limit the request. Now let's understand this algorithm with the help of an example. Firstly, we have just 2 main things in this algorithm. The first is sliding window capacity. It's pretty intuitive. This tells the maximum number of requests that are allowed in the window, similar to our maximum limit, you might recall, in our fixed window algorithm. The second would be the sliding window look back. Now, what is this? This is nothing but
how many seconds our window should look back from the current timestamp. Or in other words, it is the size of the window. For example, in the diagram, you can see that we have a look back period of 60 seconds. So effectively, the size of the window is 60. And then the maximum number of requests that we can hold in this window is 3. This is the capacity. You can see that in this window, we have one request which came at t equal to 0, another one which came at t equal to 30, and another one which came at t is equal to 60. Now let's do a run through to understand the algorithm better. We'll go chronologically from t equals 0 till t equals 110. In general, this is the approach that we'll follow. Whenever a request comes in, we first look back 60 seconds, using our sliding window, and then remove any requests that are outside this window. Also, we will then count the total number of requests that are within this window. Then definitely add 1 for the incoming request. Now, if the sum is within the limit, it means that our window still has the capacity to hold this request, and therefore this request shall pass through. But if this exceeds the limit, or in other words, our window is already at its fullest capacity, then the request would be rate limited. For example, at t is equal to 59 seconds, you can see the window's capacity exceeds 3. So the 59-second request is rate limited. However, one thing to note here is that the request at t is equal to 59 is still added to our sliding window. Why do you think this could be the case? Basically, our system tracks all the requests, irrespective of whether they are accepted or rejected. This is necessary because it will help it to decide whether to rate limit future requests or not. We know that we always look back and see how many requests have been there in the window yet. So even if the request is rate limited, it was still a request that our system got, and therefore it should influence the rate limiting for all the future requests. Enough talking. Let's come through our run through and see this in action. Let's say at t equals to 0, we get one request. What does our algorithm do? It first creates a look back window of size 60, from the current request timestamp, which is 0. And then it would remove any requests that are beyond this window. Now, in this case, this is our first request, so there are none of the requests that goes beyond this limit. Also, then we count the total number of requests in our window, which is 1. And we know that 1 is less than our capacity of 3. Therefore, this request is allowed and would be a successful request. Now let's say at t equal to 30 seconds, we get another request. Again, we create a look back window of size 60 from the current timestamp, which is 30. We remove any request that is beyond this window. There are no requests which are beyond this window. Now the next step, we count the total requests in our window, which is 1. This is already present, and 1 for the new one. The total would be 2, which is still less than the capacity of 3. Therefore, this request is also allowed and would be a successful request. Now let's say at t equal to 45, we get another request. We again do the same 2 steps, look back and remove any requests which are beyond this window. There are none of the requests again which are beyond this window. Then the second step, we count the total number of requests in this window, which should be 3 now. 3 is just the capacity but not exceeding it. So the request is again allowed and would be a successful request. Now let's say at t is equal to 59, we get another request. Looking back 60 seconds, we don't find any requests that are beyond this window. Then we count the total number of requests within the window. Now this time it would be 4, which is exceeding the capacity of 3. Therefore, this request would be rate limited. But we should still add this request to our window. Now let's say that at t is equal to 110, we get another request. First, we look back and remove any requests that are beyond this window. Now, given that our look back window has a size of 60, it will go from our current timestamp of 110 till 50. Now we have 3 requests which are beyond 50. We remove all of them. Next, we count the total number of requests within our window, which is 2. T is equal to 59 and T is equal to 110. Now 2 is again within our limits and therefore this request is allowed and is a successful request. Now you can see that even though T is equal to 59 was a rate limited request, but it still contributes to the request count in our sliding window, which should be the case because if let's say we get 2 more requests, let's say hypothetically at T is equal to 111 and T is equal to 112, then we should rate limit the last one, which is the request at T is equal to 112. This is because we already have 3 requests in our window, which includes the request that was rate limited at T is equal to 59. So basically, irrespective of whether the request is allowed or rejected, it should be added in our window because that rate limited request, in case the request is rejected, would still influence the future rate limiting. I hope it makes sense. Now this is pretty much about the algorithm. Let's now talk about the pros and the cons. One of the pros that we have already discussed is that since the window is sliding and not fixed, nobody can exceed our limit of requests by perhaps sending or squeezing the requests near the edges of the window, like we saw in the fixed window. So in short, rate limiting would be pretty precise and accurate all the time and not an approximate one. The con here is that this algorithm uses more memory. This is because, as we saw, even if the request is rejected, we still add it to our window and store that. So this means we are consuming more memory.
Now, just a disclaimer alert. We might get little mathematical here, but with example, it should be very easy to understand. Else, I will recommend you to pause and replay the videos at critical pieces to get the best feel out of it. On a super high level, if I have to summarize the sliding window counter algorithm in one line, I would say it is the average of fixed window counter algorithm and the sliding window log algorithm. Taking the best of both the worlds. So let's directly start with an example to understand all of this. We will consider a scenario. First, run the fixed window counter algorithm on it. Then we'll run the sliding window logs algorithm on it. And then ultimately we'll run the sliding window counter algorithm to see how it is taking the best of both the worlds. Consider the following situation. From 0 to 60 seconds, let's say we get 6 requests. We got 1 request from 0 to 20 seconds. We got 2 requests in the range 20 second to 40 second. And then we got 3 requests in the range 40 second to 60 second. Now from 60 to 120 second, let's say we get 3 more requests. All the 3 requests in the range 60 to 80 seconds. Also, the maximum allowed limit for the requests is 6 every minute. So 6 is our cap limit or maximum limit that we allow every minute. Now let's see how the fixed window algorithm would work out in this case. Now, as per our fixed window algorithm, it wouldn't rate limit any of the requests because in both of these windows, in both of these fixed windows, the first window from 0 to 60 and the second window from 60 to 120, in both of them, we have not exceeded the maximum count of 6. In the first one, it is just 6, and in second one, it is actually 3. But if you take a closer look, let's say on a window going from t is equal to 20 till t is equal to 80, how many requests do you see? Is it more than 6? Yes, indeed, we have got 8 requests from t equal to 20 till t equal to 80, and 8 is more than 6. So effectively, in this 60-second window, we have got more than 6 requests. But our fixed window algorithm didn't catch this. In fact, it would not rate limit anything at all. Why is this the case? We already touched on this. This is because there is an underlying limitation in the algorithm as it just looks at fixed windows. In this case, just 2 fixed windows, one going from 0 to 60, another going from 60 to 120. It doesn't look at all the possible windows in the interim. To solve this, here comes the sliding window logs algorithm. Now let's see how the sliding window logs algorithm works in this case. Now the sliding window logs algorithm will always look back from the current timestamp. So it would look back 60 seconds from the current timestamp. So let's say we are at t is equal to 80 seconds. So we look back 60 seconds from here using our sliding window. Next, the algorithm will count how many requests are there in this sliding window. Now there are 8 requests in this window, but we had a limit of 6 and hence we reject the last 2 requests. Now this works good, but the only concern here is that for this algorithm to work, we need to store all the request timestamps or quote unquote logs for all the requests in our window. This is because when it looks back 60 seconds, it needs to know which requests are falling in that 60-second window. Any request that has an earlier timestamp would be discarded. So effectively, we keep on storing all our request logs or timestamps. Now this consumes space, resources, and is not that efficient. Now let's come to the sliding window counter algorithm and see how it works in this case. Now initially, it's the same step as that of the sliding window logs algorithm. At 80 seconds, it would look back 60 seconds using the sliding window. Now there are 3 things happening here. First, we have a sliding window that goes from 20 seconds to 80 seconds. And then we also have 2 fixed windows from 0 to 60 seconds and from 60 to 120 seconds. Let's call these 2 fixed windows as the current window. The current window is the current one that we are looking, which is 60 to 120 seconds. And the previous window. The previous window is the first fixed window, which goes from 0 to 60 seconds. Now, first, it will count how many requests are there in this current window. Now, effectively, in the current window, which is 60 to 80, there are just 3 requests. So we count them. Now, for the previous window, here's the interesting thing, and here's the differences. We don't manually count all the requests that were in our previous window. The window which is going from 20 to 60. Instead, it would estimate the total number of requests that should approximately be present in our previous window. What do I mean by this? Let us see with the help of an example. By estimation, it would be pretty simple. It would first see how many total requests were present in our first fixed window. So in our first fixed window, we already know that there are 6 requests. And then it will see what is the size of the previous window. The size of the previous window is 40 seconds because it goes from 20 till 60. So assuming uniform distribution, we have approximately 40 divided by 60 into 6, which is 4 requests. So this gives us an average of 4 requests in our previous window. And therefore, the total requests in our sliding window, that is from 20 to 80, would be 3, which is requests in the current window, plus 4, which is average requests in our previous window. So this amounts to 7. Therefore, the total requests 7 would exceed the limit of 6. So our last request essentially would be rejected. Now, what are the benefits of this? Firstly, now using this, unlike the sliding window logs, we don't need to store all the request timestamps. Instead, we could just have an assumption that requests are evenly spread out and then use simple mathematics to just estimate the requests in our previous window, hence making it memory efficient as compared to our sliding window log algorithm. Definitely using averages and a mathematical formula is much faster than counting all the timestamps in the sliding window. Now you might wonder that this might cause slight errors. Example, here we see that instead of 2 requests being rate limited, we just rate limited one of them. But in practical situation, this usually works out well. By the way, a fun fact, Cloudflare experiments show that 99.997% of 400 million requests were correctly processed using this algorithm. And there was an error of only 0.003% requests that were either incorrectly allowed or rate limited. So this data shows that this algorithm in practice seems to work pretty good. Now, so far we have seen rate limiting just as a single component. But in real life, we don't just have one rate limiter. In fact, we have multiple instances of it. Plus, there are always concurrent requests happening. Concurrent requests happen around the same time. Now, let's take at one of the examples and try to understand this nuance that I will be covering. Let's say that our rate limiter receives two requests from the same user at the same time. The first request tries to read the counter value of 6 and then it increments the value by 1, which is 6 plus 1. Now let's imagine that in the middle of this process, there is a second request that comes in, which is highlighted by green in the diagram. Now our first request hasn't updated the counter. So effectively, the second request will also read the counter value of 6 since it has come before our first request has updated the counter to 7. Therefore, this request, which is the request 2, will also update the counter to 7. But in fact, our counter should be updated to 8 because there are two requests and therefore there should be two increments for that counter. Now, why is this issue happening? This issue is happening precisely because our steps 3 and step 4, as marked in the diagram, is between the step 2 and 5. Basically, our second request has come in between our first request. Our first request hasn't completed its work and the second request just comes in. Now, this issue is called a race condition. This is because two requests are racing to read and update the same value. Now, how can we solve this? It's quite intuitive. We can just use locks. Now, what is a lock? A lock means that while one request is processing, other requests have to wait. Once the first request is done, it would release the lock and then only the next request can be processed. So let's take a look at this updated diagram. We have the request 1 marked in purple. It tries to read the counter from the cache. It gets the value of 6. Now we have the request 2 comes in at step 3. This request also tries to read the counter value from the cache, but the first request has already logged this cache. Therefore, this second request has no other option but to wait. Now the first request continues and it updates the counter value to 7. Basically, only after our request 1 has successfully completed comes the request 2. You can see in the diagram that there is a step 6 at which our request 2 will be allowed. So after this, the request 2 comes. It tries to read the counter value and gets the updated counter value this time of 7. And then ultimately it tries to update the counter to 7 plus 1, 8. Now locks can solve this, but they can also slow down our system a bit. There are other methods to handle this like Lua scripts, but we'll discuss them some other time.